Currently, transformers have dominated super-resolution tasks, thanks to their ability to capture long-range dependencies and apply input-dependent weighting. Thus, many prior works have attempted to reduce flops and parameter counts, while also increasing the self-attention window size to expand their receptive field. However, despite their reduction in flops and parameter size, super-resolution transformers exhibit substantially higher latency and memory usage compared to traditional convolutional neural networks. For example, SwinIR Lite is 4.7 times slower and requires 2 times higher memory compared to RCAN, even though it requires only 17 times and 14.5 times fewer flops and parameter size. In this work, unlike prior super-resolution transformers that primarily target reductions in flops and parameter count, we focus on improving memory efficiency to enable practical deployment. To this end, we first analyze the self-attentions of the SwinIR Lite and observe that its similarity modeling and resulting features are highly consistent across layers. This cross-layer redundancy suggests that a subset of self-attention layers contributes little marginal information and is amenable to more efficient replacements. Inspired by this observation, we propose a memory-efficient super-resolution network, dubbed emulating self-attention with convolution. Our ESC follows classic residual-in-residual architectural design and employs stacked ESC blocks as a deep feature extractor. The proposed ESC block uses only a single self-attention layer, unlike prior super-resolution transformers that typically stack 6. This design substantially reduces both the number of self-attention layers and the memory-bound operations they incur, such as tensor reshaping and window masking. Additionally, each block employs 5 convolutional attention modules in place of the removed self-attention layers. A convolutional attention module is designed to emulate key advantages of self-attention, like long-range dependency modeling and instance-dependent weighting, with memory-efficient convolutions. To emulate long-range dependency modeling, a convolutional attention module employs a 13 by 13 large kernel convolution. We share a single 13 by 13 convolutional kernel across the entire model to address the parameter growth of large kernel convolution. To emulate instance-dependent weighting, a convolutional attention module includes a parallel dynamic depth-wise convolution branch. Its convolutional kernel is generated from the input, enabling input-dependent modulation with low memory cost. These 2 types of convolutions are only applied to 16 channels in front, to significantly reduce the memory access costs of convolutional attention module. Taking a step further, we adopt flash attention to mitigate the prohibitive memory access costs of self-attention. By not materializing the whole score matrix using flash attention, we substantially reduce latency and enable larger attention windows. For the classic super-resolution task, which upsamples bicubic downsampled images, our 3 ESC variants exhibit better latency performance trade-off, or even flops performance trade-off, compared to the representative super-resolution convolutional neural networks, transformers, and state space models. The visual comparisons demonstrate that our ESC also restores visually pleasant results. Local attribution map analysis demonstrates that our ESC extracts long-range features, despite the fact that most self-attention layers have been replaced. We further analyze the convolutional attention module on 3 aspects. First, feature map visualization demonstrates that the convolutional attention module extracts structural features similar with self-attention. Second, gradient visualization exhibits that the shared 13 by 13 convolution extracts longer range features than dynamic depth-wise convolution. Finally, similarity visualization shows that dynamic depth-wise convolution extracts more input variant features compared to the shared large kernel. Lastly, we evaluate our ESC on large-scale datasets and super-resolution tasks, such as arbitrary scale super-resolution and real-world super resolution, to verify that reducing the number of self-attention layers does not sacrifice data scaling ability or representational power of transformers. Thank you for your time and attention. If you're interested, please check out our paper and code.